just briefly on the website to recap what we're going to do. As I said, I kind of do the sessions, lectures, then practicals, and I think that seems to work best for the online courses. So I'm just, but I will leave breaks, which I know it's a bit heavy, but I will leave breaks. So I'm going to go through the Pi solution first, then talk about non-blocking communications, then collective communications, and then after the break, we'll have a solid practical. This afternoon, I'm going to do virtual topologies. My colleague Mark, I have to leave at about 2:30, but my colleague Mark, who was around yesterday, will do the derived data types, and another colleague, Adrian Jackson, who's also who is an expert on MPI as well, will cover the practical session. So it's a few different people today, unfortunately, just due to the way things have worked. So if I then go to the course materials, what I want to do is to go through the Pi solution. So the solutions I provide are typically quite brief. I have really quite a detailed solution to the Pi solution, which is this one. So what I'm going to do is I will share I'll go through this. Now, please ask questions here. It's quite important. I wanted to go through to try and show what this shows. So if I can find the right window, I think is that one. Okay, fine. So what I'm going to do first of all is I'm in / right place. I'll wget that file, is the Pi. I'll untar it. And I go into the directory. See that there are 4 directories. Now, normally I go through the C and C++, but I think there's a slight majority of Fortran programmers, so I'll go through the Fortran one first. Okay. So, as I said, there seems to be a reasonable number of Fortran programmers, so I'm going to go to the Fortran exercise. Give me a second if I just get all my windows set up. Okay, fine. So here we are. So if you look, there is a make file. So I'll look at PySerial.c as well. Serial to F90, sorry. It's kind of obvious what it does. It just, I have n, I have pi, and I just saying, the code is very, very simple here. Like from n, pi is pi plus 1 over all this stuff here, just the formula, and then I multiply 4 over double of n, and I also compute the exact pi, which is 4.0 times arctan 1.0, and I print pi minus exact pi. One of the errors that people make is they do something like at the end they'll do pi equals pi times 4 over n. Okay. What's 4 over n if n equals 840? Zero, exactly, because it does integer division. So yeah, that's a classic. You have to be careful on these things. That's a classic thing. So let's compile that. And run it. And actually get really quite, so 341 from 1592, it's really quite close. You know, it's the percentage error is, you know, it's 1 part in 10, 100 million accurate, which is astonishing given such. Anyway, so that's fine. Now let's look at this, the parallel one. So I'll make the window a bit bigger. Let's just check that yeah, that looks fine. So first of all, I have to use MPI. Okay. Always do implicit none. I've got the same thing here, and now I have MPI variable, so I'll move these down a bit. So I have com, which is an integer, rank, size, source, tag, IRA, and here I have my status, which is dimension MPI status size. And I'm going to split up the iteration space, so I have an I start and an I stop, and I also have some extra variables to do partial pi. Now, I deliberately do a print here before MPI init, And the reason is to emphasize what somebody pointed out yesterday, was that MPI is parallel from the start. I mean, you wouldn't do this in a real program, but you will get multiple statements there. You know, you have multiple programs running that are launched by srun or MPI run or whatever your job launcher is, and all the MPI init does is let them get together. I do MPI com size, com rank, and I do hello from rank whatever just to make sure, and then I have the standard. If we just say rank is 0 running on that. Okay, now, so as I say, I assume the n is divisible by a number of processes here just for simplicity. And I'm splitting the iteration space up into chunks of n over size, where size is the number of processes. And so I start is n over size times rank plus 1, and I stop is I start plus n over size minus 1. Now, the code only works if you get I start and I stop correct. And I've often seen people stare and stare and stare at the code. You know, just print them out. Yeah? Print on rank whatever. Now you have to print on rank whatever, otherwise you won't know what the other I start is blah, I stop equals blah. Print them out, and that allows you to debug this program. Then the loop is just very simple. Everyone loops over there. So this is a example of SPMD, single program multiple data. Every process is running identical code, okay? But they don't do the same thing because different processes have different I starts and I stops. And remember, different processes have different partial pi's. We only have one. We've only said double partial pi. We've only appear to have declared one partial pi. But every process has its own. You know, each process has its own partial pi, its own private copy. And so that works. And again, I'm printing out what the values are. And now, as I say here, you should really use a reduce. But what we'll do is, first of all, let's look. This is if rank equals 0. Let's do what everyone else is doing. So let's go down to the bottom. Okay. So this is what rank not equal to 0. All other processes send their partial value to rank 0. So I put a print statement here. I'm just setting tags to 0. MPI send partial pi, which is 1 double precision, to 0 with tag com and I error. And actually, I haven't shown this, but if you look at the com, I set com equals MPI com on here, just to show you that that you can do that. So that's everyone other than rank 0 sending to rank 0. And then, of course, rank 0 has to. Now, we conventionally pick rank 0 as the controller. There's nothing special in MPI about rank 0. It's not like OpenMP. In OpenMP, thread 0 is special. Thread 0 is the same as the process, the parent process, the main program. Rank 0 is not, there's nothing special about rank 0, but we conventionally need a controller. Rank 0. Rank 0. That's the controller. Why rank 0? Why is rank 0 a sensible choice for the controller? Although there's something special about rank 0. We could pick rank 7 or rank 13 or whatever. But if we want to control a process, we normally pick rank 0. What would be the problem about printing rank 13 as the controller, for example? Quite a simple reason. So it's an obvious choice, but there's a why not print rank 13? Absolutely, you always have a rank 0. That's the important point. So so that's why it's a very sensible thing to do. It's convention, but it's also sensible because there is always a rank. Like Michelle's right, there is always a rank 0. So what I'm doing is I'm looping. I have to do size minus 1, receive do source equals 1 to size minus 1. Now, I am not actually, I'm receiving from any source here. MPI receive pi, which is 1 double precision, from MPI any source, tag com status I error. And the reason I've done this is really just so I can show you how to say who I received from, right star, comma star, rank 0 receiving from rank, and its status MPI source. That will say who I'm receiving from. And then I add in to my running total, and then I print out the answer at the end. So let's just make file. Oh, it's set up for that. Okay, right. So we should just be able to make, and I should be able to now. I will. Is there a job file? No. So I'll copy. I'll have to edit the ARCHER2 MPI job. Well, actually, I could edit this. So I will this basically I could do node equals 1 task equals, I don't know, 16. I have to do 184 here, and I have to change it to be high parallel. Test batch ARCHER2 MPI.job. I had this command wrong in the sheet yesterday. I said it was s batch minus u. It's sq. I've corrected that. Should be finished. And let's look at the answer. So as you see, this print was before the MPI init, but we get 16 of them. Then we get hello from rank 0. And if we look, this looks correct. On rank 0, istart is 1, istop is 52. Now you'll see that the output here is ordered from rank 1, 2, 3. That is not guaranteed. The output can, I'm surprised it's like that. The output normally can happen in any order. It's unusual for the output to be ordered like this. It must be a feature of Slurm. But you'll see that, okay, so I got the wrong answer, and the reason I got the wrong answer was because I was being stupid, is that 840 is not divisible by 16. So let's do 20. So that was why I got the wrong answer, because I picked a number which wasn't divisible. So let's see when this finishes. CG seems to mean exiting or something. I don't really. Okay. Hello, obviously something else. 38823.192. So it'll be the same thing at the bottom. We get the right answer here. Okay, so apologies. However, actually, it's running interactively is quite nice. So you'll see on the crib sheet, I gave you the sort of semi-interactive way of running. So I've cut which is 5 parallel, and I want to maybe say I just cut this. Whoops, this isn't going to work because of the reservation isn't correct. But let's this command comes straight from the crib sheet. So this allows me, let's run on 4. This allows me now to watch it running in semi-real time, and that's sometimes more useful when you're developing. Okay, so we can see it actually running, and you'll see that it works. Now, one thing I wanted to show was that if I run on, say, 20 tasks, okay, and I just want the answer. So I'm going to just I'm just going to get the answer here, but we won't see this running. All I want to show you is the answer here. I'm running on 20 tasks. It'll take a little while, but we'll see the answer there. Okay, so this is the answer here. Okay, and I run again. And I get exactly the same answer. Let's try again. We're not guaranteed, so I'm trying to show you can sometimes get a slightly different answer. There we go. We've got a very slightly different answer here. Okay. Why do we get a slightly different answer? Anyone hazard a guess? Yes. So the serial program would always give the same answer. So you're right. Yes, but it is different, and that's worrying. So why did it give? Yes, floating combination. So that well, so not associative actually. A plus B plus C. But why? So you're absolutely right. Floating point addition is not associative. It is mathematically, but not in finite precision. But that's absolutely right. But why did this give a different answer? So the calculations are happening in a different order. Why are they happening in a different order each time I run the code? Because the serial program wouldn't do that. The serial program would give exactly the same answer every time. I'll show you the code. Yes. So if I just, there we are. So if you look, that's absolutely right. So if I basically, it's because I do them, and if I grep into, okay, if I grep into receiving, you'll see which order it receives, because it's doing. So I'm doing MPI receive of any source. So I'm receiving any order. So here it received from 15, 1, 3, 11, 5, 2, 9, 4, blah, blah, and the next time it will be a different order. 15, 1, 3, 11, 5, 12. The next time it is 2, 5. So it is, that is a bit of a problem. The way to fix it, well, the natural thing to do is actually just to do MPI any, rather than do from MPI any source, but to receive from actually receive from source. So I receive it in a prescribed order, yeah, and this will now give me the same answer each time. This will give me the same answer each time I pause it. I'll run 3 times in a row, but because it receives in a set order, so this should give you the same answer every time. Now, okay, that's just something to be aware of. Yeah, so this is going to give me the same answer every time. And actually, if I do, you'll see that it will do exactly what you expect. It will return. It will do it receives a new order 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is fine. Now, the fact, and this code looks quite simple, but the fact that it works is really quite subtle, actually, because, you know, in the code, we have, if I maybe can get them both on the screen at once. In the code, yeah, we have one receive. Sorry, I'll do the loop here. We have a loop. We issue size -1 receives. We appear to only issue 1 send. But the point is that one process does size -1 receives, and size -1 process do 1 send. So, you know, if you make any mistake in this at all, you're going to get deadlock, or at least the wrong answer. So let's say, for example, source equals 1 to size -2. Yeah, okay, fine. Let's do, if I do, I run now, there's a bug in that program, sorry. Now, this is why running interactive is quite nice, because when you get deadlock in a batch job, it's not quite clear what's happening. So this has produced the wrong answer, but the code is not finishing. So what's happening here? Okay, this has produced an output. So remember, I missed one of the receives. Okay, so I've done one too few receives. So the code has finished. Sorry, produced an output, but it's not finishing. Any ideas why that is? What's happening? Why somebody's stuck and they're not getting to MPI finalized? Who do you think is stuck? Yeah, well, rank 19 is waiting. Rank 19 is phoning and nobody's picking up. So rank 19 is basically is not working. Or yeah. So I mean, so that's an interesting. I will now go to the C version, it's very, very similar. Oops. Okay. It's just basically identical, except we have hash including MPI.h. The variables are not integer com, and they're MPI com and MPI status. It looks very similar. There's not really any difference here. I've done exactly the same. You have to be careful and see that you do mean I'm going from 1 to n, so you have to be careful about your loop limits. The lower limit isn't 0, the lower limit is 1, so you have to be careful about that. Other than that, it's fine. Well, because, right, so rank 0 asked for 18 messages. It got them and it printed out its answer. It got what it wanted, it got 18 messages. The problem was, so rank 0 was happy, it had received 18 messages. The problem was there was a 19th message not received. Does that make sense? So what was happening was that rank, no, not at all. It's not obvious at all. Ranks 0 to 18 were sitting in MPI finalize. Everyone waits MPI finalize. And they're all sitting there saying, where's rank 19? Rank 19 is wherever you guys got. So that's how it. So this is very similar in C. There's really no difference here. It's identical code, except the status is it's status.mpi source here. Okay. Now, what I did want to show was for the now I purport to have a C++ example here. It's not really C++ because I'm not a C++ programmer. It is just C with C out. It just shows you how to do it. Really, it isn't anything. So it's not really very. I mean, it's really the only reason I really did it was to give you a make file actually to show you how to compile with CC. But the interesting one is Fortran 2008. I'll go through that. But the interesting thing about Fortran 2008 is you have to use a different module. Okay, use MPI FO8. Okay. Now you'll see that the MPI variables are identical to the C ones. Instead of MPI com, it's type MPI com, type MPI status, type MPI data. So it's a lot nicer. The code is really the same, except the IERA variable is now optional. So I don't need to put that IERA variable in. That would be a mistake in the normal and if you look at the receive, I'll leave that stuff now. The status is, again, just like C, it's a member of the status structure or derived type, as MPI, as Fortran calls it, status percent MPI sources. So the Fortran 2008 interface is just the C interface with a few brackets on it, and it's nice. I do like it. I did go through this stuff about the real size. So Fortran has a very sophisticated type system. So if you say to Fortran, could you please give me a floating point number which has this many units of decimal precision in it, how do you know in MPI whether you should say MPI real or MPI double precision? Well, there's a way of saying to MPI, okay, there's a variable called pi, tell me how big it is in terms of bytes, and then give me an MPI real type, which is the right size. It's slight magic, but I wanted to put that in here. Some of you have problems getting that to work. We should check, but that that's just if you're a Fortran purist, then this is what you want. This is what you want to do. Okay. Okay. So I thought hopefully that was useful. Does anyone have any questions on that? So I think when you're developing code, the interactive srun is actually quite useful because although the syntax is very verbose, it does mean if you get a deadlock, you actually see it happening. Whereas if you submitted this to a batch job, you would just see the batch job running out of time and you'd be like, what's going on? So yeah, I think I think it is useful to do that. But I would encourage you to print debugging information to the screen because it's not obvious, but 673, 714, 715, 7, yeah, this is all correct. So what we'll do is I'll take a few minutes. I'm do the just 3 minutes, just so if people want to take it, I will. Just so people can take a little break, I need to go and get some more water. Okay, so you can see what happened here. You didn't see that. But what happened is that I set a timeout of a minute, and so within a minute the job crashed and got killed. So that's why you should set sensible timeouts in your batch jobs, because if your MPI job deadlocks, you still pay for the time. So that's one of the reasons you should put sensible timeouts. Otherwise, you pay for all that time. Okay, so I will just be 2 seconds and. So there's a question. No, okay, so I understand the issue. So I shall share the. That is a very good point. So I won't share the. So I'm just trying to get too many things here. Can you hear me, Christoph? Just check that, yeah, that I'm not. You're back. Yes, fine. So what happens at the send? Okay. Where's the send? Okay. Oops, sorry. Is there send here? Okay. MPI creates a message here, which has a payload of one double precision number, but also has some metadata, which includes the tag, who's the sender is and stuff like that. So the message that's sent down the network is more than 8 bytes. It's probably something like 120. It'll be some packet size, like 128 bytes. So if you want MPI to buffer that with MPI buffer attach and MPI bsend, you need to provide enough memory for that whole message, which is the metadata plus the data. However, on the receive side, you specify 2 storage areas. That's for the data and that's for the metadata. So the data goes in there and the metadata. So yes, you do specify more than 8 bytes for the receive, yeah, but you specify it separately. The data goes there and the metadata goes there, and then we're able to print it out here. Does that make sense? So the amount of storage you have to provide for the receive is more than 8 bytes, but you provide it separately because it's much easier. Okay, fine. Okay, that was a good question. So what I'm going to do now is give the next lecture, which is on non-blocking communication. And give me a second. We saw yesterday that there was a problem with deadlock, that if you used MPI send, it was difficult. You had to be careful arranging your sends and receives to avoid deadlock. I warned against using MPI bsend, but the problem was if you used MPI send, you might be lucky, but you cannot guarantee that it is that the MPI send is asynchronous. So you have to assume it might be synchronous. So we have a problem. The problem is, how do we avoid deadlock with synchronous send? And so the way to do it is to do do something called non-blocking. So the fundamental problem we have with well, I'll talk about it actually when I get the right cursor. not very happy. Okay, well, we'll have to just live with that. Right, so what we're going to do is we're going to look at a pattern, and I don't understand why it's not working. We're going to look at a pattern where we're going to send data around in a ring. And this is actually going to be the exercise we're going to do. We're going to consider a bunch of processes. They're numbered slightly strangely here, but we have 6 processes here, and we basically want everyone to send a message to their neighbor. And if you think about it, that's exactly the communications pattern we have in the traffic model on a roundabout. Okay, that's why where everybody sends to the neighbor and receives from their other neighbor, but you do it you close the loop. Okay, so it's a complete ring of. Now the problem is if you try and do this with synchronous send, okay, if everyone issues the receive first, then everyone is receiving, everyone is waiting for the receive, okay, and nobody is sending. So if you do receive from your neighbor that way, send to your neighbor that way, you get deadlock because everyone is receiving and nobody's sending. If you use synchronous send and you do synchronous send to your neighbor that way and then receive that way, you get the same problem. Everyone is doing synchronous send, waiting for the receives to be posted, but there are no receives. So the problem is you really want to have the receive and the send operating at the same time. But the problem is you have to do one before the other. And if you do the receive first, you get deadlock. If you do synchronous send first, you get deadlock. And therefore, by definition, if you use standard send, you might get deadlock. So there's a problem here. But what non-blocking communications allow you to do is to have multiple message passing operations, both sends and receives ongoing at the same time. And that means that you can break the deadlock. There is a simple way to break the deadlock here. The numbering isn't very helpful, but you know, if you can you think of a simple way in the traffic? How could you break the deadlock here? If everyone sends first and nobody receives, you get deadlock. If everyone receives first and nobody's sending, you get deadlock. Can you think of a way of breaking the deadlock and ordering things so that you can break the deadlock? Reverse the order for one, yes, but it needs to be not just for one. You've got the right idea, but it's not just for one, really. You're absolutely right. You want to reverse the order on some of the processors, but which ones? Yes, exactly. Oh, exactly. So absolutely, even ranks receive, odd ranks send, and then you reverse. That's exactly the way to do it. However, again, that doesn't really generalize. So for this simple 1D problem, it does. It's a potential solution. It becomes very difficult for the generic problem. So, oh, that's better. Okay, fine. So MPI talks about the mode and the form, and we've talked about. I'm just going to basically very quick this. I don't understand why my cursor isn't working. I will. Give me a second. I'm just going to try. Let's see. My PowerPoint seems to have something of an issue here, which I don't understand. So let's just try it again. There we are. Okay, fine, we're better now. So the mode of a communication determines when its constituent operation is complete. That's synchronous or asynchronous. So synchronous send only completes when the message has been sent. Asynchronous send completes immediately. However, MPI also talks about something called the form. The form of an operation determines when the procedure implementing that operation will return. Now, when control is returned to the user program. Now, when you call a function like a square root, if you do y equals square root of x, you expect that when the square root returns, then you've got the answer. However, what we're going to do here is we're going to have calls which are non-blocking that return immediately. What we're going to do is we're not going to do a message passing operation. We're going to initiate. What we're going to do is we're going to say, could you please start sending a message, or please start receiving a message? Return control to me immediately, and I will later on come and check that that operation is completed. So we have things called non-blocking operations. A blocking operation blocks and waits till it's completed. A non-blocking operation just initiates something and comes back immediately. And so blocking operations relate to when the operation is completed. And a blocking operation only returns from the subroutine call when the operation is completed, like you'd expect. If you call synchronous send, when it returns, it has done the send. If you call receive, when it returns, the receive is completed. What we do with non-blocking operations is they return straight away and allow you to do something else. So what we do is, instead, if we think about the synchronous send as being sending a fax, rather than going up to the fax, putting the fax in the machine and waiting for the beep, we have three phases. We now have an initiation phase where we start sending the fax, a completion phase where we come back and check it is completed. But in the middle, we can do something else. Okay, so instead of saying I want to send a message and I'm going to wait for it to happen, we're going to say to MPI, could you please start sending that message? I'll go away and do something else, and sometime later I'll come back and check whether it has completed or not. The important point is, people immediately think that this is a way of hiding communications overheads by doing computation here, but actually what we normally do here, the most useful thing is to actually issue another communications operation here. So what we could do in the message around the ring example is we could say, could you please start sending a message to my neighbor up the way, return control to me immediately. I will then go and receive a message from my neighbor down the way, and then I'll come back and wait until the message is going up the way. So that allows you to have more than one message passing operation going on at once. And that's the fundamental reason why you can break the deadlock. You can have multiple message passing operations in happening at the same time, and that can break the deadlock. So all non-blocking operations should have a matching wait operation. Sometimes people, say, could you please start sending this message, and they never come back and test it's been sent. That's a dangerous thing to do. Non-blocking operations are not magic. Some people suddenly think, oh, by using non-blocking operations, I've broken the deadlock. They're not. They're not magic. They give you the opportunity to break the deadlock. But if you do a non-blocking operation immediately followed by a matching wait, it's simply equivalent to a blocking operation. If you just say, could you please start sending this message, and by the way, I'm now going to wait for it to complete, you have achieved nothing. What you have to do is you have to say, please start sending this message. You have to go away and do something else. You have to use that as an opportunity to issue another operation and then come back later. And non-blocking operations are not the same as sequential subroutine calls. The operation continues after the call has returned, and that gives you some issues, which we'll talk about. So you separate the communication to three phases. You initiate the non-blocking operation. You do some work, perhaps involving other communications, and yes, that's what we're going to do, and you wait for the non-blocking communication to complete. So a non-blocking send is a bit like having an outbox, okay? So it's not a perfect, but it's a bit like saying, rather than me saying to MPI, here's a message, I don't know if you can see me, here's a message, could you please send that, and I'll wait until it's sent. What you say is, here's the message, I put it in an outbox, okay? I'm going to go away and do something else. And when you come back later, you check, I'll wait till that has been sent. A non-blocking receive is very much like having an inbox. Instead of saying, I'd like to receive a message, please, and waiting forever, what you say is, okay, I'm expecting a message. When it comes in, could you put it in there? Then I'll go and do something else, and later on I'll come back and check or wait for the message to appear. So that is so the only reason why the inbox and outbox the outbox analogy isn't necessarily 100% is there are no copies taken. Okay, and when you do non-blocking operations, there are no copies. So you say to MPI, there's my message, could you please send it sometime in the future? There is no copy taken. It's sending the actual message. Okay, there is no copy taken there. So imagine, I think a good analogy for non-blocking send is sending a message via a parcel via a courier. So I have a parcel here that I want to send via a courier. So I go to DHL or somebody, my favorite courier, and I say to them, here's my parcel, could you please send it? Okay, so I give them the parcel and I give them some money, but they give me something back. What do they give me back? So I say, please send this message either online or physically. A receipt, yes, But what does that receipt allow you to do? It's more than a receipt. A partial ID, absolutely. They give you a tracking number. So you say, could you please send this message, this parcel? They give you a tracking number, and later on you can come back and check if it's arrived. So MPI gives you the same thing. When you initiate any non-blocking operation, MPI says, right, I'll start that, and then it returns to you a tracking number, an ID, a receipt. It calls it, I could think of it as a ticket. It's up to you to remember that ticket, okay? You have to remember that ticket. And so MPI calls it a request. So for non-blocking communications, the data types are the same, MPI data type and COM, but you get a request, an MPI request, an object of type MPI request. MPI calls it a request handle, or it's an integer in Fortran, which is this ticket. So MPI gives you that ticket, and later on they say to MPI, remember this communication, has it finished yet? Could you wait for it to finish? So non-blocking synchronous send is very similar to the blocking version, but it has first of all, it's not MPI send, it has MPI send. That is supposed to indicate that it returns immediately. So this routine will return, this routine initiates something, it returns immediately. So you have buff count data type, data type, comma, exactly the same, but you have to pass it a pointer to a request, which is then returned to you. Later on, you can say, okay, I've done some stuff, I now have to wait for that send to count, and you can then wait. MPI waits until that request has completed. Oh, the status isn't particularly important here, but you say, could you please wait until that request is completed? In Fortran, it's just the same, except the request is an integer. Okay, MPI wait. Now, if you write this, MPI ISend, MPI wait, you have achieved exactly nothing. But the important point is, because they're separate functions or subroutines, you can now put your own code in there. MPI I receive is a bit like MPI receive. Instead of doing it's MPI I receive. So instead of saying I want to receive a message, you say I'm expecting a message. When it comes in, put it into this buffer. So you provide a buffer, you provide everything, but then MPI returns control immediately, and you remember this request, this ticket. So you can later come back and say, remember that non-blocking send that I issued? Has it completed yet? And MPI remembers, MPI just has one type of request. MPI remembers if it's a send request or a receive request. However, so we've added an extra parameter to this receive here, which is the request, but there's something missing. What is missing from that receive? A blocking receive would have an extra argument in there, which isn't there. We've told it where we want to receive the data, okay, but there's something missing here, which would be there in a normal receive. The status, exactly. So why is there no status? Why doesn't it make sense to put the status here? What does the status tell us or give us information on? The status gives us information on the metadata. It gives us information on the actual message that was received. But by definition, this routine returns immediately before the message has been received. So we defer the status to the MPI wait. Okay. So when you wait on a receive request, you say, please wait until that receive is completed. And when it completes, the data will appear here, but the metadata will appear in the status here. Okay. So the status isn't particularly relevant for a non-blocking send. Fortran, it's just the same. Okay. So blocking and non-blocking, send and receive can be blocking or non-blocking. A blocking send can be used with a non-blocking receive and vice versa. You can use any mode, synchronous, buffered, or standard. And it's slightly subtle, so I'll talk about it. So okay. So synchronous send, okay, we saw that synchronous send could give you problems with so that's absolutely right. I'm gonna, yeah. Yes, so MPI, so okay, so I'll answer those two questions. MPI IS send achieves the same thing as MPI B send, okay, in the sense that it allows you to send messages without the danger of deadlock. Okay. However, MPI bsend is horrible and ugly, and you shouldn't use it. So we would, so you, also you're absolutely right. The MPI ISend does not take a copy. So it's, you know, so that's maybe quite nice that you don't have a copy. So that's right. MPI ISend achieves the same thing as MPI bsend, but without there being a copy. So it's slightly more syntax. You have to issue it, remember the request, and wait later on. Does that make sense? Yeah. So will the message eventually be received in the buffer if I do not call MPI wait? Well, you don't know. The problem with not calling MPI wait is, okay, so if I do a receive, I say to MPI, I'd like to receive a message, okay? When it comes in, could you put it there? If I look at that buffer without doing a wait, I don't know if it's the new or the old data. So it's unsafe. It's completely unsafe to look to do anything unless you call the wait. So yes, the message might arrive. It might not. You don't know, and because you don't know, then you can't do anything with it because you don't know if it's the new or the old data. Yeah. So because synchronous send can have problems with deadlock, you use Okay, so I'll come back to that. Okay, that's a very good question. You've hit on exactly the problem. This is where non-blocking operations are more complicated. That then it's undefined. If you change, so again, if I was important enough to have a secretary, I'm not, and I had a letter, I might say to my secretary, I might say to him, look, I've written this letter. Okay, could you please take a copy of it, photocopy it, and send it off to somebody. Okay, so take a photocopy of that message, okay, and then send it. If I then alter it without asking my secretary whether he's done it or not, I don't know if he sends the unchanged or the changed version. So you get undefined behavior if you change the buffer. That's a dangerous thing to do, and you get subtle undetermined runtime errors or undetermined runtime behavior. Does that make sense? So you must not do that. Okay. Because receive is synchronous, you get problems with deadlock. So you use iReceive. Because standard send can be synchronous, you have to use iSend to safely program. Okay. Now, buffered send exists because non-blocking buffered send exists because the people who wrote MPI were very completist, but it's a pointless routine. Okay, you would never ibsend because if you use bsend, then you don't have any problems with deadlock anyway. So why would you use ibsend? So it's just there for completeness, but no, you would never use it. But in this course, you should program with isend and iReceive in the exercises. That's what I want you to use. So you can also you can test. Okay, MPI waits until a request has been satisfied. MPI test gives you a flag true false in Fortran 10 in C, which says has it completed. So you can say has anything arrived yet, and if MPI says yes it has, you can then read the data. Okay, and you get a little flag back. So this is an example, a very contrived example in C, but just to give you the syntax. I'm going to send data, a send array from 10 integers from rank 0 to rank 1, but I'm going to do it in a non-blocking way for no apparent reason, just to show you the syntax. So I need a request object and a status. If rank equals 0, I do MPI ISend, the send array, which is 10 integers, to 1 with the tag, with the com world, and I remember the request. Okay. Then I call a function called do something else while ISend happens. And later on, I have to wait for the send to complete. Otherwise, I don't know if I can, I don't, exactly as what Jacobin is saying, how do I know when I can overwrite the send array or alter it? I have to call MPI. I'm only allowed to touch the send array after I've called MPI wait. Okay. If I'm rank 1, I want to do an iReceive. I want to receive into a receive array. I do the same thing, MPI iReceive. Receive array 10 integers from 0, tag Commonwealth request. I then call a function, do something else while iReceive happens. And then I have to wait for the receive to complete because I'm not allowed to look at the receive buffer until so I do an MPI wait request status. Now, this request is different from this request, okay? This wait is waiting for the send to complete. This wait is waiting for the receive to complete. There is no concept in MPI of an end-to-end message, okay? So you have to be careful. This is waiting for the send to complete. This is independently waiting for the receive to complete. Now, because it's synchronous, they'll sort of complete at the same time, but they're different things. This request is not the same request, okay? This request is the send request on rank 0. This request is the receive ticket on rank 1. They're different. You have a different send ticket and a receive ticket. In Fortran, it's just the same, except it's an integer request, and I have an I error, but it's all exactly the same. So you might have multiple non-blocking communications. If I have this controller worker situation, I originally said, I'm waiting for a message from one of you guys. I don't know who's going to complete first. I would issue a receive with MPI any source. What I could actually do is I could have a separate inbox for each of you guys. So I might have an inbox, a non-blocking receive. I have lots of inboxes waiting for all your messages. In that case, I want to test multiple non-blocking communications. I want to say, look, I want to maybe wait till you've all completed. I want to say, have any of you completed? Maybe say, have you completed? Or so there's lots of things you can do. The syntax gets very complicated, but you can wait or test for completion of all messages. MPI wait all, MPI test all. So you supply an array of requests and an array of statuses, and it waits or tests for all of them to finish. This is what you would do with halo swapping. The best way to do halo swapping, someone mentioned halo swapping in 2D, you have to send a message up, send a message down, send a message left, send a message right, receive up, receive down, receive. What you do is do them all non-blocking. Non-blocking, send up, down. You have 8 non-blocking, and then you just say wait until they've all completed. Okay. You can test or wait for completion of one message, so you have an array of requests, but you only have a single status because it will wait until any one is complete, or if any are complete, and return to flag. And there's a test or wait for completion of as many messages as possible. MPI wait some, MPI test some, and the flag get the syntax. You can understand what you're saying. I've got all these non-blocking operations. I'm going to wait. Could you wait until some of them have finished? Then MPI has to tell you how many have finished, which ones they were. So you have arrays of requests and statuses. You have lots of flags. The syntax gets quite complicated, but you can understand. You're saying to MPI, could you please wait or test until some of these have finished, and tell me which ones have finished, and then I can carry on. Those basically exist. Okay, fine. So here I mentioned, you will see a lot of program. So the problem we had with the message round a ring example was if we had the send, we never issued a receive. If we issued the receive first, we never issued the send. There is a routine in MPI called MPI send receive, which solves that problem by you supply all the parameters for the send and the receive in the same function call. So this is just all the parameters for the send and the receive stuck together in one big function, okay? And this breaks the deadlock because it allows MPI to have them both going at once. However, so in simple pairwise communication patterns, it's useful, but it does not generalize. And so I would not recommend programming with MPI send receive. I don't think it's a useful routine. It's a shortcut, but you should learn how to use non-blocking properly. If you use send receive, it's a bit of a dead end, that it solves the simple problems but doesn't generalize to more complex ones. So I'm not a fan of send receive, although you will. I mention it because you may see people using it. Okay. So the exercise is to, we'll do this after the coffee break, is to rotate rotate information around a ring. We're going to arrange processes in a ring, and each process sends a copy of its rank at an integer variable, and you communicate them. I'll go through this actually in more detail when we actually do the exercise. But what we're going to do is we're going to do a global sum here, and we're going to do it by sending the data around in a ring, as opposed to the controller worker thing we have where everyone sent the data to a single controller. But I'll go through this in more detail at the beginning of the practical session, because I wanted to complete the lectures now. So I will talk about this more when I introduce the practical at 11 o'clock. So that's that lecture complete. I was going to wait another 5 minutes till I do the next lecture, which is collective communications, but does anyone have any questions on that? It's quite a lot to take in, but I think the analogy of sending a message by a courier is a useful one. Please send this message, give me back a ticket, and I'll come back later and check whether it's completed or not. And you can have multiple ones going on at once. If you have multiple non-blocking operations, you have to remember multiple tickets. It's up to you to request to remember them. Okay. If you have 4 non-blocking operations at once, MPI will have given you 4 tickets, 4 requests. So, okay, send receive basically is if I wanted to do a send up the way and a receive down the way, which is the pattern for message around a ring, okay? If I issue a send first, then I may never get to the receive. If I issue the first, I may never get to the send. MPI send receive issues the send and the receive at the same time, and so breaks the deadlock. So you just specify all the parameters for the send. You just specify the parameters for a send and a receive at the same time. So this is just all the send parameters and all the receive parameters stuck together into a big horrible routine. Does that make sense? And MPI will make sure that they both happen at the same time. So it's just like issuing a send and then a receive, but you do them at the same time, and it then avoids the problems of deadlock because you're not ordering them, you're issuing them simultaneously. So there's 2 very good answers here. It's odd that you may specify different send type and receive type. So that's in a normal situation, the send count and the send type are the same as the receive count and the receive type. But when we use derived data types, which Mark will talk about this afternoon, it's more subtle than that. 99% of the time that you use this, you will have send count equals send type and receive count equals receive type. Yes, sorry, send count equals receive count and send type equals receive type. However, there's a slight subtlety with well, I'll tell you. You can define the data type, which is a block of 4 integers. Okay, so send count could be 1, and the send type could be a block of 4 integers. Receive count could be 4, and receive type could be integer. So they're compatible. Do you see? So it's a bit more subtle than that. Kerry, is it just a wraparound? Yes. If you download OpenMPI and look at their implementation of MPI send receive, it's I send, I receive, wait. I mean, that's all it is. Yeah, nothing magic about it. So you're absolutely right. It is just a wraparound, a non-blocking send and receive. So there's nothing magic about it. So I don't think it's particularly useful, but a lot of people seem to like it. So we'll take another 3 little break, just so we have some. I'll give people a reasonable break. That's that 10. Okay. Just a few minutes, just so people can. I'll take a little break and be back. So just to say, Christoph asked what happens if you do this. Do you mean what happens if you specify different send type and receive type? Is that I don't think I answered that question. Christoph asked about what will happen if you do this. I didn't quite understand that. Sorry. Maybe I'll just wait a couple of seconds. Just checking the audio is okay. Oops, I can't. I'll just clarify that it's reasonably okay. Fine. Okay, good. So I'll just wait a couple of minutes. I appreciate. I'm going to be slightly over time. Apologies for that, but this is quite a short lecture, so. No, it's fine. Sorry. I mean, that's what I did as well. So. Yes. Okay. So If they were compatible, it would be legal. In other words, if you specified sending one block of 4 integers and receiving 4 integers. But if they were incompatible, i.e. you sent one double precision and received 17 characters, then the behavior, like everything, is undefined. MPI might spot, it might not. It depends. So, for example, yesterday somebody no, they didn't do that. They did something different. But anyway, okay. So I'll now give this lecture on collective communication, which is relatively straightforward. Apologies, I might be a few minutes over for the break, but so when you've done the message around a ring example, you will have implemented summing up distributed data in 2 different ways. One is by sending it onto a controller who adds the data up. The other one is with sending it round a ring so everybody sees all the data. But no, they're both very useful programming exercises. But in fact, if in a real program to do this, you would use collective communication, such as reduce. So again, MPI was designed right from the get-go for real large-scale parallel programs. And it realized that there's often cases where you want communications involving a group of processes. So a collective communication has to be called by all processes in a communicator. That might mean MPI will be using everybody in MPI com. Well, it means everybody, but technically it has to be collective across a communicator. The example, use a barrier, broadcast, scatter, gather, and global sum and global maximum. The things which are done all the time in parallel programs, I think, are global sums, and I'll come back to that. But I'll go through the first ones quite quickly. Characteristics. It's a collective action over a communicator. All processes must communicate. So one of the biggest mistakes people make is they say, if rank equals 7, call MPI reducers. That's not going to work. It's a bit of technicality that synchronization may or may not occur. But what you should imagine is, in your mind, you should think that a collective communication has a barrier. Oh, sorry. Apologies. We should. Thank you. I've forgotten to. The share didn't work. I was just saying, the collectives are the ones I talked about here. I'll cover them here. But the characteristics are all processes must communicate. That means every process has to call the collective operation. So you can't say if rank equals 7, call a broadcast on MPI com. Well, that's not going to work. Synchronization may or may not occur. But in your mind, you should think of there being a synchronization. Everyone does what they're doing, like a broadcast, or adds all the numbers up. There's a synchronization at the end. Now, for optimization, MPI may not do the synchronization, but I think it's safest to think of there being a synchronization. That makes it very clear to you, if one process omits to call the collective, you'll get deadlock because they're all waiting for him or her to turn up. The standard collectors are blocking. There are non-blocking versions. I say recently, actually, this is many years ago into MPI 3. It's an obvious extension of the blocking version. You call a collective, you get a handle back. But to be honest, they're not that useful, I don't think. We can discuss that. There are no tags, and the receive buffers must be exactly the right size. I mean, the reason that we have so when you do send and receive, if you send more data than you receive, MPI will say error, incoming message too large, for example. When you do a collective operation, you're going to be specifying lots of send buffers and receive buffers. MPI does not check they're all the right size. The reason is it could, but the reason we have collectives is for efficiency. We want to add up a double precision number across 5,000, 100,000 processes. We want that to be done quickly. If MPI did lots of checking, it would spend all its time checking everything was okay and none of the time doing the calculation. So it's because, so this is where, ease of use is sacrificed for performance. MPI does not check very much here because it knows that you want these to be done quickly. It's there for performance. So barrier synchronization into MPI barrier. Everyone waits until they enter the barrier and then they all leave. We can discuss this later, but actually barriers are almost never used in MPI because every routine, be it send, receive, or the other collectors, do the appropriate synchronization. However, the time you use a barrier, and I mentioned it in the exercise sheet, if you want to time them, you don't know what MPI processors are all running at different speeds. If you want to time a piece of code, it's very useful to get them all to start. So you'll see barriers. I put barriers in codes when I want to do timing. I'll say, look, everyone line up on the start line. Let's start the timer and then wait for everyone to finish. But you should not be using barriers in real codes. If you are, you probably don't understand what you're doing, other than for timing. Broadcast is much more useful. Broadcast you do at the start of a calculation. So imagine rank 1 here has read in some data, A, B, C, D, E, and we want to replicate it. These might be the simulation parameters, replicate it across all processes. So A, B, C, D, E is replicated across all the processes. That's a broadcast. Okay. So what you do here is MPI broadcast, buff, count, data type. So here, buff would be this array here, count would be 5, and data type would be whatever these are, MPI integers, for example. And the root is who has the data at the start. So on entry, and here it would be rank 1, the root has the data. On an exit, everybody has the data. So it basically copies the buffer, which is counted. It's like doing a point-to-point send from everybody to from the root to everybody, but it's much quicker, okay? Because it can be done much more efficiently. Is that clear? Okay. So this is broadcasting. So yes, file I/O is pitifully slow. It is much, whereas the network bandwidth is much higher. So yes, you should not. Your standard mode should not be lots of people opening a file. It might even crash the file system. Imagine you have 100,000 processes opening a file. Do you think a file system can cope with 100,000 open file handles? I don't think so. It'll probably crash. So yes, you should nominate somebody to read the file. For small data, for big data, it's different. But for small amounts of data, when you want it to broadcast, yes, one person should open the parameter file, read the data, and then broadcast the data to everybody. Does that make sense? If it's simulation data, it might be different, but yes, you should not have everyone opening the file. Scatter is a bit like broadcast, except, well, when a process exits MPI bcast, then its buffer has been completed, right? So when you return from MPI bcast, you have the data. So it doesn't mean that everyone has. This isn't reading. Sorry, this isn't. I said this data might have come from, but this isn't reading. Okay, what I meant was this process has read some data from file, but it has 5 integers. Okay, I don't care where it could have read them from file, but it has 5 integers in an array. It wants to copy them to everybody else. It calls a broadcast. Okay, so there's not any reading here really. Okay, but when you exit the broadcast, then you have completed what you want to do. So if you're the root, it means that your data has been sent to everybody. If you're not the root, it means that you have received the data. It doesn't mean that everyone's received the data. It just, no, you specify the name, okay? So, you remember, just like a receive, you say where it's, so no, it's not the same variable name. Everyone's specifying the same buffer, yeah? I think read as a, imagine I did a broadcast. Imagine we were sitting in a classroom, okay? And I had a printed sheet, okay? So the exercise sheet was a printed sheet, okay? We would all execute a broadcast. I would go and give you all a copy of the exercise sheet, okay? When you exit the broadcast, you have a copy of the exercise sheet. It doesn't mean that everyone else has a copy, but it means that you have a copy. That's all you care about. Why do you care if everyone has it? Yeah. Why do you care if other people have it? You don't care, okay? You just care you have the copy. Does that make sense? So, yeah, fine. No, they're not in the same variable name necessarily. You could call it what you want. So you could say it would. The natural thing would be to be int x, yeah. If rank equals 0, x equals 53. Yeah. Imagine this is two processes. MPI bcast x1 MPI. Okay. That'd be the natural thing to do, yeah? Whatever, okay? But you could do, yeah? Let's just say this true process. If I equals 0, it's stored where you will call it. So in this case, in what I've just typed there, the 53 is stored in rank 0's x, rank 1's x, rank 2's x, rank 3's x. Everybody's x is set to 53. Okay. Remember, the x exists on every process, so they're separate. So the first if rank equals 0 only sets x equal to 53 on rank 0. The other x's are undefined. After the broadcast, all the x's are set to 53 on every process. Is that clear? But it doesn't have to be. Yeah, it doesn't have to be. Yeah, there it is. But you could actually specify different variables if you wanted. But yes, by default, it's the simple case. It's the same variable. Yeah. Sorry. Oh, I see. There's no in buffer and out buffer. Yes, yes. There's no in buffer and out buffer. Sorry, I understand the question. A scatter is saying, well, when MPI bcast is complete, then you are complete. You have the data, or you've sent the data. So it's sort of like neither really. It could be either. Yeah, I could do a broadcast by phoning you or sending you a letter, but basically, yeah, you don't know, and you don't care. All you care is when you exit the broadcast, what you were supposed to do is completed. In other words, if you're the root, then your data has been sent off, so you can carry on. If you're not the root, your data has been initialized to what it should be, so you're fine. So all you care is that it's done. The operation is completed. How it's implemented by MPI is up to MPI, and that's deliberate. MPI can implement it any way it wants. Just means that when you exit the collective operation, whatever you need to do is finished and over, and you can then carry on. Is that okay? I'm being slightly technical here, but it is important. You shouldn't really bother about how it's implemented. It doesn't matter. It could be either. So if MPI bcast was implemented by sending an email, yeah, when the root exited MPI bcast, it would not mean that everyone had received their data, but you don't care. If MPI bcast was executed by doing a phone call, then when the root exits, then everyone will have received the data, but it doesn't really matter. It could be either. When the root exits MPI bcast, all it knows, it's done everything it needs to do. That might mean that the data will get there, but it might mean the data has got there. It might mean it hasn't. But you don't care. You've finished. You can carry on. Because when you exit the bcast, what you need to do has been finished. Yeah, your variables have been initialized. You don't care if someone else's variables are initialized. Yeah, if I give you your worksheet, yeah, in the classroom, you don't care if the person over there has got their worksheet or yet. Why would you care? You've got yours and you can carry on. So your variables have been initialized. Yeah. Yes. Yes. Bcast has to be every collective. So the bcast has to be called. All collective operations have to be called by every process. Yeah. Everybody is calling bcast. Everybody is calling bcast. Yeah. 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 But within that, you have different roles. The root sends the data and the other are received. Sorry, I understand the confusion. Yes, so everybody has to call a broadcast. Yeah, everybody here calls MPI bcast. If they didn't, then it would be impossible to transfer the data from here to here if this guy didn't call bcast, because they would be doing something else. You can only transfer data in message passing with the active participation of both sides. For send and receive, that means actively call send and actively call receive. For broadcast, so for collectives, it means everybody has to call the collective. Is that clear? Maybe that's the clearer way of saying it. Yeah. Scatter is like broadcast in some sense, except the data is split up. This is what you want to do for the traffic model. You would have an array of 5 cells, A, B, C, D, E, but on output, instead of broadcasting A, B, C, D to everybody, the first person gets A, the second person gets B, the third person gets C, then D, then E. So you're scattering up into blocks. And so the syntax is MPI scatter, send buff, send count, send type, receive buff, receive count, receive type. And the root, everybody has to call this, but the root is the guy who has the data. Now, imagine we're doing integers here, okay? I have a send buff, which is this guy, a receive buff, which is this guy. What do you think send count and send type and receive type are MPI int, for example? What do you think send count and receive count are in this example? It's not obvious at all. So in the scatter, I specify a send count and a receive count. What do you think send count and receive count are for this scatter to work properly? Yeah, you'd think it was send 5 and receive 1, but it's not. It's send equals 1, receive equals 1. So send is, the count is how many each the count is the size of the small message, okay? So if you think about it, yeah, this function never says explicitly how much data to send. It will be send buff would be the buffer, send count 1, MPI integer, receive buff, receive count 1, MPI integer. How does it know here that there are 5 items? I haven't told it there are 5. Where does the 5 come from? So MPI knows that there are 5. But how does it know that? It knows because we call this, yes, exactly. If we call this on com world, MPI says, Michael's called it on com world. Com world has 5 processes, exactly. So it assumes, trusts you that you made this buffer 5 long. If you haven't, then all hell breaks loose. But okay, so actually it's implicit in the size of com world. Okay. Gather's just the opposite, so I won't go into any detail. It's exactly the same. Again, send count and receive count, other side of the small message. So, so the basic scatter and gather routines are quite restrictive. They do a fixed amount of data transfer between every pair of processes. All data seem to be contiguous in the larger array. So basically, all you can do is you can say, I mean, I could scatter, I could do send count equals 2 and receive count equals 2 and send A, B here, B, C, D here, E, F, G, H, I, J. But they're very restrictive. There are more general versions called vector versions, called scatter V and gather V, where you specify different counts for each process in different locations. So you can send different amounts to each process from different locations, but you need these scatter V and gather V, where you have to specify more stuff. If you can do even more complicated things. So yes, if process 1, yes, so if process 1 scatters the data, the send buffer is untouched. Yeah, the send buffer is untouched. It keeps a copy of the full data set. Yes, it does. However, by far the most common thing you do is a global reduction routine. So I will. Is it okay if I just carry on? Maybe 5 or 10 minutes to finish this lecture now. Is that okay? I should do a poll. Sorry. Okay, fine. I just worried that people had some. That's fine. Okay, and we'll just take a longer lunch break. Okay, so I think that's good. Okay, fine. Thank you. We've seen. Fine, I understand. Okay, that's good. That's clear. I just wanted to check. Okay, fine. So so we're going over time, but that's because people have asked some really interesting questions. That's a good reason for going over time. Global reduction operations you do all the time. For example, imagine a weather forecast simulation. I split up the map of Great Britain amongst 100 processes. Each is simulating the weather over a square, and it computes the rainfall. The rainfall over a random square of the United Kingdom is a meaningless number. The only number is the global thing. We saw this the pi example. The incomplete sum, the partial value of pi, was a meaningless number. So you always end up doing this thing where each process computes a local sum and you globally reduce it. Now you can do lots of reduction operations, but you can do sum or product, but in fact sum is the one that people do all the time. But you can do maximum or minimum or a user-defined operation. So there's only one reduction operation, MPI reduce, just like there's only one send operation, MPI send. But you tell MPI what you want to do. You tell it if you want the max, the min, the sum, the product, logical or min or max. Okay. So max, min are obvious. Sum is the one you do all the time. You can do product, you can do logical operations. Max lock. If I wanted to find out who the oldest person in this course was, probably me, I could take a maximum of our ages. That would tell me what the maximum age was, but not who it was. Max lock tells you what the maximum age is, what the maximum value is, and who it is. It gives you a rank as well, which can be useful. But these are the obvious things you want. So the function is MPI reduce, an input buffer, an output buffer. This is the input, this is the output. A count, which is how many elements there are, a data type, an operation, which is something like MPI sum, and a root is where the answer is placed. So for example, when we did our pi calculation, we were sending all the data to rank 0. Who got the so the root there was rank 0. Only rank 0 got the answer. So MPI reduce takes the data, combines it, and puts the answer on a single process, which is the root. So everyone has to call this. Everyone has to supply a send buffer, but the receive buffer is only initialized on the root. So an example is probably easy. So people get confused about the count. Okay, so this is actually not such a good diagram because I have 4. The count is not the number of processes. Okay, an MPI reduction operation implicitly takes place over all the processes. The count is the number of items. So what I'm saying is, if count is, so if I have 4 processes and they specify, they each have a little array of size 4, which is called A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Well, I'm calling the operation circle here, but think of it being addition. If I do an MPI reduce with root equals 1, then the receive buffer here is set to A plus E plus I plus M. This one here is set to B plus F plus J plus N. So the count is the number of items you're reducing, but it's implicitly across everybody. Now the count is often 1. You're often just reducing a single scalar, but it can be more than 1. And I'll give an example here. So here's an example of global reduction. We want to add up X to get the result. So MPI, if everyone has to call this, everyone has to say, we're adding up all our X's to get a result. It's one integer. And what's this reduction of? We're going to add them together. We're going to sum them. And the answer will be placed on rank 0. So the sum of all the XI's is placed in result. The result is only placed there on process 0. So this is how we could do the pi summation in a single call. However, okay, so I'm just trying to. Okay, sorry, I do have that slide. Sorry, I forgot where my slide was. You can do user-defined reduction operations. You can say to MPI, I want you to reduce these values and don't use max, min, sum, product. Use this function I'm going to provide. Now, so what you have to do is you have to define the function, register it with MPI, and tell it to use the function. So the syntax is quite involved, but hopefully, I'm not going to cover it here, but hopefully the concept is quite simple. There are a set of predefined reduction operations, max, min, sum, product. If you want to do your own, you have to write a function and tell MPI about it, and it will use that function. but they can be quite fun. But I'm not going to cover that here because it's just a bit of syntax. There's a question here. So what do you mean by assumed shape arrays? This syntax, as I say, where do you mean here? Here again, this is a pseudo. This is old-fashioned. It's just saying it's no. They can be anything. They can be any array. Yeah, this is just a. Yeah, this is actually probably an old prototype. Actually, this is the sort of Fortran 77 prototype. Sorry, it can be anything. Yeah. So MPI all reduce. There's no root process. So MPI all reduce. The answer goes everywhere. So actually, that's often more useful. MPI reduce scatter, the result is scattered. I've never used. MPI scan is a parallel prefix, and I'll cover that. So I'll tell you what. So for example, MPI all reduce often, if you wanted to add up this array A, B, C, D across all the processes, MPI reduce places the answer on a single rank, all reduce places the answer everywhere. So everyone's third value is set to C plus G plus K plus O. Okay, and actually MPI all reduce is often what you need. So MPI all reduce is just like reduce, but there is no root because the answer all reduce takes the input, which is count integers, say, and adds them all up if you're doing MPI sum and sticks the answer in receive buff, but it sticks it there everywhere. Okay, and so that's often what you want. So it all reduce, take X and place a result, add up one integer across everybody, and sum of all the X values is placed in result. The result is stored in every process. Now, what I'm trying to show here is, imagine I have three variables: pressure, temperature, and rainfall. Okay, I could call MPI all reduce on the pressure on one double precision, MPI all reduce on the temperature, which is one double precision, and MPI all reduce on the rainfall, which is one double precision. You should not do that. Okay, if you have three things to reduce, you should stick them in a little array and call an MPI all reduce of all of three of them. Okay, on the array. Okay, so the reason why do you think that is? Okay, what takes the time in doing reduction on? Yeah, well, it's yes. So what do you think takes the time? So I'm doing an all reduce over 100,000 processes. Okay, 100,000 processes are going to have to communicate with each other. Okay, then they send one integer and add it together. That takes no time at all. Okay, so an all reduce of three integers will be 3 times quicker than 3 all reduces of one integer. Okay, because sending 3 integers and sending 1 integer takes the same time. Adding 3 integers and adding 1 integer takes nanoseconds. It takes no time at all. Okay, so you should. It's like if I told you to buy 3 liters of milk, you wouldn't drive to the supermarket, buy a liter of milk and come back. Drive to the supermarket, buy a liter of milk and come back. Drive to the supermarket, buy a liter of milk and come back. You drive to the supermarket. Once you got there, you buy 3 liters of milk. Do it all at once. Okay, so that that is one of the classic optimizations in MPI. Do reductions of vectors, not scalars. Okay, because all the time is in the communication and the coordination, and none of the time is actually in sending the data. Sending 1 integer or 3 integers takes the same time. Adding 1 integer is the same, makes no difference. In C, it's just the same answer here. So it's just to give an example. MPI scan is like MPI reduce, all reduce, except MPI all reduce would add A plus E plus I plus M on everybody. MPI scan only it stops. So I should know this. Yeah, inclusive. Okay. So what was the question? Larger buffers. I mean, you're not saying larger arrays. What do you? Well, MPI takes care of all that. So, I mean, you can all reduce a gigabyte a megabyte if you want. I mean, so I mean, an MPI will take care of it. So, it will have to use some intermediate storage, but it will just do it all for you. I mean, you don't have to provide it. Yeah. Okay. Does that make sense? So MPI takes care of all that for you. MPI scan is like reduce, except instead of getting A plus E plus I plus M, here you get A plus E, A plus I, A plus I plus M. It stops. Okay. I've never found that. There's a few times. It's something which you might want to do. So MPI scan is an integer partial sum, the same syntax as on reduce, but it only goes up to you. So on rank 4, you get the answer on 0 plus 1 plus 2 plus 3 plus 4, but not the whole thing. So exercise 5 on the sheet is to rewrite the pass randoming program to use MPI double reduction. It's a single call, okay, MPI or reduce, but it's just there. So sorry I've overrun. I think we should maybe let's take the full break. We have, you know, so I have over an hour for the practical. Okay, so if we could, I'm happy to take questions now. Actually, sorry I overran slightly, but let's take a break to 11:50, and the practical will be 11:50 to 12:30. Okay. Is that okay? So any. The correct way to add up all these numbers is to use an or reduce, but we're going to do message round a ring because that illustrates the correct use of MPI of non-blocking communications. And then what an interesting thing to do with the or reduce is to see how much faster it is. It will be much faster than what you can do by hand, but that's just that's on the exercise. Okay, so if not, then we'll take a break now and